In the first video, we talked about the concept of the atom, the smallest uncuttable particle that comprises matter. We talked about how over time different elements were discovered, and this led to the concept of the periodic table, which was conceived by Dmitry Mendeleev. Let's continue. Each of the elements, 118 or so, has a name and a symbol, a 1 or 2 letter abbreviation. H for hydrogen, He for helium, Li for lithium, etc. What makes one element carbon and another nitrogen and another fluorine? The elements differ in terms of the number of protons, electrons, and neutrons. Shown on the right is a typical representation, like on a periodic table, of the element carbon, where we show that it has 6 protons, and we also show something called the atomic mass units, 12 in this case, which is the sum of the number of protons and neutrons. Now, we haven't really explained what protons and neutrons and electrons are, but we have to start somewhere. So here's the table of elementary particles, protons, neutrons, and electrons. And in this table, I give you their relative mass in something called AMU units. A proton being about 1 AMU, neutron also about 1 AMU, and an electron being much smaller, approximately 1/2000th of the mass of either a proton or neutron. I'll also give you the relative charge, +1 for protons, -1 for electrons, and neutrons 0, of course, because that's why we call them neutrons. Now, what is an AMU unit? An AMU unit is the way to represent the mass of a proton, or neutron, or electron. And if we can convert this to grams, it's a very, very small number. 1 AMU unit is equal to 1.66 times 10 to the minus 24th grams. Now, to give you some concept, in our most sensitive balances, we can measure maybe 1 times 10 to the minus 5th, maybe 1 times 10 to the minus 6 grams. So protons and neutrons and atoms in general are so small that we cannot measure them by putting them on a balance, the way we measure the mass of regular quantities of material. Because atoms and these subatomic particles are so small, we really just can't weigh them out. So we have to talk about their mass in the relative units called AMU units. Similarly with charge. Our concept of charge is probably not as well formed as our concept of mass, but the elemental charge can be expressed in terms of coulombs, coulombs being a measure of electrical charge, and the elementary electrical charge is 1.60 times 10 to the minus 19th coulombs, also a very, very small number. Now, to help you wrap your mind around these numbers and what they mean, why some are relative and some are sort of absolute numbers. Consider an M&M. This is a plain M&M, and a plain M&M has a mass of approximately 1 gram. It's actually 0.91 grams on average. But let's say an M&M weighs 1 gram. You notice that they're all really M and not M&Ms, because there's only an M on them, but I digress. So you have an M&M with a mass of 1 gram. Now, below that, I show a dot. Let's consider this to be sort of an elementary particle or proton dot, having a mass of 1.66 times 10 to the minus 24th grams. And the question is, how many of those little elementary proton-type dots would be needed to put together 1 gram of an M&M? Well, it would be some number times 1.66 times 10 to the minus 24th. That number x times 1.66 times 10 to the minus 4th would be 1 gram. If you solve for that, you'd get x is equal to 6.02 times 10 to the 23rd. Oh, now that number 6.02 times 10 to the 23rd, which is essentially the inverse of the mass of an AMU unit, that is something called Avogadro's number. Avogadro's number, named after the scientist and lawyer Amedeo Avogadro. Actually, his full name was Lorenzo Romano Amedeo Carlo Avogadro di Corregna e di Spoleto, and he first described the concept of this number which we now refer to as Avogadro's number, which is oftentimes referred to as a chemist's dozen. Okay, and here's why. Again, we cannot measure the mass of a single atom of an element or the mass of a molecule very well. Now we can measure some, but in general we don't have balances that can measure on the scale of 10 to the minus 24th, 10 to the minus 23rd grams. So instead we want to scale up. So instead of trying to weigh out one atom of an element, for example, one atom of carbon, instead of that we scale up to Avogadro's number size, and we weigh out 6.02 times 10 to the 23rd atoms of carbon. We'll see a little later that Avogadro's number of atoms of carbon weighs 12 grams, just like Avogadro's number of protons would weigh 1 gram. Okay? Now, to give you an idea of how large Avogadro's number is, I compare it to the U.S. national debt in 2016. We think our national debt is tremendously large, but look how much larger Avogadro's number is. Okay? So again, the concept. It would take Avogadro's number of these elementary particles having a mass of 1 AMU, 1.66 of 10 to the minus 24, to make up 1 gram, like 1 gram of an M&M. We said in the first video lesson that ancient Greeks, Leucippus and Democritus, had a concept of an atom, but then it was kind of lost for a couple thousand years. But then experiments by scientists including Lavoisier, Proust, and Dalton led to what is called the atomic theory, and we usually refer to this as Dalton's atomic theory. And some of the important type of laws that were discovered along the way were, one is what is called the law of conservation of mass. And the way to explain that is if you have 3 grams of hydrogen will react with 14 grams of nitrogen to form 17 grams of ammonia. That is, they're additive, and the product weighs the sum of the 2 reactants. Okay, so that's the conservation of mass. Also, there's the law of definite proportions. Again, if we stick with our example of ammonia, regardless of the source or means of preparation of a compound like ammonia, it will always contain nitrogen and hydrogen in the mass ratio of 14 to 3, 14 grams of nitrogen per every 3 grams of hydrogen. It's always in that proportion of 14 to 3. So this is what the law of conservation of mass and the law of definite proportions refers to. These observations led Dalton to conceive what we now call the atomic theory in 1808. And the 4 tenets of the atomic theory are shown in this slide. 1, each element is composed of tiny indestructible particles called atoms. Back to Leucippus and Democritus. Okay, finally we return. 2, atoms of a given element have the same mass and other properties that distinguish them from other elements. That is, the atoms of carbon will have a particular mass and particular properties that distinguish carbon from nitrogen and oxygen and lithium and sodium. 3rd, atoms combine in a simple whole number ratio to form compounds. That basically means water is H2O, 2 parts of hydrogen combining with 1 part of oxygen, or ammonia is NH3, 1 part of nitrogen combining with 3 parts of hydrogen. 4th, atoms of an element cannot change into atoms of some other element. That is carbon. Carbon cannot be converted to oxygen. Now, we will see a little later on when we talk about nuclear chemistry that we can convert the nuclei of some elements to others, but that's outside of the realm of normal chemistry. But in normal chemistry, atoms of one element remain that element, but in a chemical reaction, atoms only change the way that they are bonded together with other atoms. That is, oxygen can be bonded with itself to form O2, or oxygen can react with hydrogen to be bonded to hydrogen to form water. So the atomic theory of matter. So the studies of Lavoisier and Proust and Dalton and others led us back to the concept that there were these smallest particles, or atoms of elements, but it didn't tell us what these atoms look like. And so there were 3 important experiments that we'll talk about which helped us visualize what we think atoms look like. The first experiment was J.J. Thomson's cathode ray tube experiment. cathode ray is a stream of negatively charged particles. We call them now electrons, but at the time they called them cathode rays. And they can be deflected by a magnetic field. If you've had any physics, you've heard of the theory of electromagnetism, the relationship between magnetic fields and charged particles. And J.J. Thomson found that if he shot a stream of cathode rays past a magnetic field, that the path of the cathode rays would be deflected, sometimes back and forth if the magnetic field were oscillating. That then was evidence that the cathode rays were charged particles. And he was able to determine from this type of experiment the charge to mass ratio of the components of cathode rays. And again, cathode rays were electrons. We now know them to be electrons. And this charge to mass ratio was minus 1.76 times 10 to the 8th coulombs per gram. Okay, so J.J. Thomson's experiment determined the charge to mass ratio of an electron. But it was a ratio. It wasn't the charge of an electron or the mass of an electron, but the ratio of the charge to mass. The next experiment was that by Robert Millikan, the oil drop experiment, where he measured the charge on small droplets of oil going through an apparatus such as shown here. And he was able to extrapolate to determine the charge on individual electrons. And that's because the oil droplets had charge, multiples of integer values of charges, and he was able to extrapolate down to only one charge per oil droplet and determine that value to be minus 1.6 times 10 to the minus 19th coulombs. So from Millikan's oil drop experiment, he was able to determine the charge of an individual electron. Combining this with the charge to mass ratio from J.J. Thomson's experiment, he was then able to also determine the mass of an individual electron, that's shown at the bottom, of 9.1 times 10 to the minus 28th grams, an extremely small value for the mass of an electron. And of course, the charge of an electron is an extremely small value, 1.6 times 10 to the minus 19th. The third experiment was Ernest Rutherford's gold foil experiment. So from Thomson's experiment and from Millikan's experiment, we were able to determine the charge on an electron and the mass of an electron, and similarly, the charge of a proton and the mass of a proton were determined. But how the protons and electrons and neutrons, which were also discovered, how they combine together to form an atom was still not known. The prevailing model at the time was what was called J.J. Thomson's plum pudding model, in which the electrons and the protons were thought to just be sort of glommed together in some spherical mass. Well, Ernest Rutherford performed an experiment that cast doubt upon the plum pudding model. He was able to take gold and roll it out or hammer it out to be very, very thin, and he then shot a beam of what are called alpha particles. Now, alpha particles turn out to be the nucleus of helium atoms, and they're positively charged. Again, we'll get to that later, but he shot these very small subatomic particles at very thin foil of gold. Now, he thought that maybe all of these alpha particles would bounce straight back, but instead he found that the majority of the alpha particles shot straight through this gold film, and only occasionally would some bounce back at an acute angle. This led Rutherford to develop the more modern atomic theory, which is that an atom has a dense positively charged nucleus containing protons and neutrons, that electrons, which have very little mass and are negatively charged, fly around a nucleus in some type of orbit, and that the volume of an atom then is mostly empty space, and also that the number of electrons is equal to the number of protons, resulting in a neutral electrical charge for an atom. So this more or less solar system model for an atom can explain Rutherford's experiment, because most of the time the alpha particles would shoot straight through the atom, because most of its empty space filled only by the electrons that are flying around in these orbits, and only occasionally would the alpha particles hit the nucleus and then bounce back. So to summarize this video lesson, atoms are made of subatomic particles, protons, neutrons, and electrons. The experiments just described led to the experimental determination of the charge and mass of electrons. Similarly, the charge and mass of protons and neutrons were determined. The results are shown in this table. Now here I give the mass in kilograms and previously I gave them in grams, so you just move your decimal place by 3. But the mass of a proton is 1.67 and a little bit more, 1.67 times 10 to the minus 27th kilograms, or times 10 to the minus 24th grams. And the mass of an electron is much, much smaller. And in relative AMU units, a proton has a little bit more than one, approximately equal to 1 AMU unit. Likewise, a neutron approximately equal to 1 AMU unit, and an electron is much smaller, about 1/2000th of the value for the proton and neutron. We say that they have relative charges of +1 for a proton, 0 for a neutron, -1 for an electron, and then in absolute Coulomb values, that would be plus 1.60 times 10 to the minus 19th coulombs for a proton, and minus 1.60 times 10 to the minus 19th coulombs for an electron. So these are the main subatomic particles comprising atoms and their basic mass and charge in both absolute and relative values. We'll pause now, and then in the last video lecture for this chapter, we'll talk about isotopes and average atomic mass units and ions. See you in a little while.